Today we study circuits. First we consider single loop circuit. EMF. EMF originates from electromotive force. So EMF. But now we use EMF instead of electromotive force. The reason is that EMF is electrostatic potential rather than force. It is not a force. The reason is force and potential has different dimensions. So we do not use the word electromotive force anymore, and we use EMF. An EMF device shifts the potential of a charge carrier by an EMF. This is negative, this is positive. So potential, electrostatic potential, the terminal, plus terminal is higher than the terminal of negative terminal by electrostatic potential E. That is EMF. An EMF is not a force but a potential difference. A battery, electric generator, solar cell, and fuel cell, they are all EMF devices. The EMF E is defined by the work done by the EMF device to the charge dq. But W is work, so it's energy. W equals Q, dW equals dQ. dQ V. So there's a potential difference. Potential scale is EMF and charge. So work divided by charge. Work divided by charge is the EMF. So EMF is the dimension of potential. An ideal EMF device lacks resistance. But in fact, EMF has its own resistance. Current in a single loop circuit. We can compute the current in a single loop circuit. Single loop circuit means a circuit made of a single loop. This is a loop. By making use of the energy method. Energy method. So energy. This work applied to small amount of charge dq can be obtained by multiplying the EMF. So the energy is supplied to this circuit by this EMF, and this is the amount of work. Here dq passes the negative to positive terminal. So energy gain dW equals E times dQ. And energy is supplied. The energy is consumed by the resistor. Consumes the energy. So power is IV, and the potential is V equals IR, so IR, so I squared R. So resistor consumes the energy per unit time by I squared R. This is dW, power supply. Power consumption. So supplied energy is spent by the resistor. Energy gain, energy loss. The magnitude should be the same. We can compute the current in a single loop circuit by making use of the potential method. Consider a single loop circuit in which resistance R is connected across an ideal battery with EMF E. Here we use the energy method. Now we use a potential method. So the difference between the potential and energy is charge. We scale out the charge to consider the potential only. In a single loop circuit, the current I is the same throughout the circuit. So current I is flowing in this direction. Here, current I is flowing. In the resistor, current I is flowing. In the wire, current I is flowing. And then everywhere, current is invariant in a single loop circuit because there is no branch and there is no charge accumulated. In a single loop circuit, current I is the same throughout the circuit. Loop rule. It's called Kirihof's Voltage Law, and when you travel along a closed loop, your electrostatic potential changes step by step. Here, from A is rises up, electrostatic up, potential goes up, and it's flat. Let me draw. This is A, B, C, D. A, potential from A has some potential. Let me call this V0, and it rises up when we pass the battery. Suddenly rises up, and this amount is V0 plus E, that is EMF, and then you pass B and C and D. Still the same, but when we pass the resistor, potential goes down. And we return to the same potential. And this one, same potential. Here, potential is the same. Here, potential is the same. Same. So up and down. So potential goes up when we pass through the battery from the negative terminal to the positive terminal, and potential decreases as we follow the line follow the direction of the current along the resistor. Anyway, when you make a complete the loop, the potential at this point should be the same after we return to the same point. So A, B, C, D. D is actually the same as A. So when you return to make a complete loop, then the potential is invariant. That is called the Kirihof Voltage Law or loop law. States that the sum of the potential difference around the circuit, sum of potential difference is the total net potential difference around the circuit vanishes. Okay. Resistance rule states that the electrostatic potential across the resistor delta V changes by IR. If you follow the direction of current I, then potential decreases. Delta V is negative if you travel opposite. I is flowing in this direction, then delta V from here to there, delta V is negative. EMF rule states that the electrostatic potential across the EMF devices changes by plus minus E. So if you travel along this direction, plus E. If you travel in opposite direction, your change in the potential is minus E. After traversing a complete loop and returning to the initial point, the potential is again the same. All right. Internal resistance. Until now, we considered the case the resistance is outside the EMF device, but it is also in practice, EMF also contains some resistance. So we assume the internal resistance of the EMF device is small r, and explicit resistance of the resistor, external resistor, is to be capital R, and let the current I flowing. A single loop circuit contains a battery of EMF E, and internal resistance small r is spread out in a line. So we draw this circuit in a straight line, and actually this A is the same as this point. So as we pass from the negative terminal to positive terminal, potential rises up. And there's a small resistance. So when we pass the resistor, potential decays. And when we pass the wire, potential is flat, doesn't change. Assume this no resistance. and then there's a resistor of capital R, so potential decays. The amount of potential loss in the internal resistance is IR, and the amount of potential loss when it passes through the external resistor is I capital R, and the total potential loss is I small r plus capital R. This one must be the same as this one, the gain and loss. So E minus IR minus IR. After you make a complete loop, then you return to the same position, and if you put this potential of the point A to be VA, and this is the potential difference from here to there at the same point, and you reach the same electrostatic potential. Because these two are the same, they cancel. Finally, you have R plus R. From here, current I equals E over capital R plus small r. If there is no internal resistance of the EMF device, it is just E over R. But because of the resistance of the EMF device, the denominator is modified like this. Resistance in series. We use the same rule to find out the current in a single loop circuit consisting of an EMF device and 3 resistors. If we repeat the same computation from this point A, the potential is VA at this point. Potential increases by E, and potential decreases by I R1, decreases by I R2, decreases by I R3. When you return to the point A, your potential return to VA. VA cancels, so what you have is E equals I R1 plus R2 plus R3. So E equals I times something. We say this is R equivalent. This is equivalent resistance. Although we used 3 resistors, it can be treated as a single resistor having the amount of equivalent resistance, REQ. The equivalent resistance of this system, these 3 resistors connected in series, we have R equivalent with R1 plus R2 plus R3. We can extend this idea, generalize this one to the case of connecting N resistors in series. then we have this formula. It can be extended to Rn. That is sum over J that runs from 1 to n Rj. Okay? So if there are n resistors with resistance R1, R2, R3 through Rn, then the equivalent resistance of the serial connection of n resistors is this. Because current I, because there is a single EMF device, current I is E over R equivalent, that is E over R1 through Rn, and potential difference Vi in each resistor is I R. Let me replace this one, Vj, Rj, because R is here. We have Rj sum over Rj, J runs from 1 to n, times E. Okay? Next, we consider potential difference between 2 points. First, minus plus. Here, delta V equals plus E. We write E. Right? From negative terminal to the positive terminal, potential differences plus E. If it is a resistor R and current I is flowing, then potential difference delta V equals I R, but we have to put negative sign on it. Following the current, the resistor spends energy, so potential decreases. When I is positive. Potential difference across the real battery. Real battery, we have considered the internal resistance of a battery. The potential difference between 2 points for EMF when it crosses from the negative terminal to positive terminal, the potential increases by the EMF. When we cross the resistor along the direction of the current, potential decreases by IR. In opposite direction, potential increases by IR. Potential difference across the real battery. We can follow the previous calculation for the internal resistance small r contained in a battery. This is a battery. Internal resistance is small r, and external resistor, capital R. So current I is flowing in this direction. Potential difference E has been increased, but IR has been decreased. So E minus IR is the potential difference between the two terminals of a real battery. If there is no internal resistance, this IR disappears. And this is the potential decrease after crossing the external resistor, and it returns to 0. So resistor current I is E over R plus R. This is the current. And potential difference between the two terminals of the external resistor is IR. And because this is I, therefore this value is the potential difference between the two terminals of the external resistor. As capital R goes to infinity, it approaches E as R goes as a small r over capital R approaches 0. The power consumed by the internal resistor and external resistor, both are expressed I squared times resistance. So internal resistor has resistance small r, external resistor has a resistance of capital R. So, and I is given here. We substitute I here and there to find out the power consumed by the internal resistor and external resistor. Grounding a circuit. This figure shows a point A. This point A. Point A is same as this wire. There's no potential difference at all, but we have a certain potential. But this single point can be connected to the ground of the earth. Then the absolute value of the potential is set to be 0. So grounding connects the circuit to a conducting path to Earth's surface. Grounding at A sets V as 0 absolutely. Power, potential, and EMF. Let V be the potential across the terminals of an EMF device of EMF E, internal resistance small r, and current I. The total power capital P supplied by an EMF device to the charge carriers is power, IV. And V this EMF, pure EMF is E, but EMF contains internal resistance, and we have seen the potential difference, and here is E, but this potential difference is E minus I small r. and E minus I small r is the capital V. This is pure EMF, and this is a potential difference between the two terminals. First is a battery, so this one. This is V, because there's actually a small internal resistance. Okay. And power is current times potential difference, and the current is flowing. Current I is flowing outside, and potential difference between the two terminals of rear or EMF device is V. So I times V is the power. So this minus IR squared, this power is lost in advance inside the EMF device because of the internal resistance. The power lost by the EMF device is this one. And total power of EMF device is this one. And so EIE is sum of IR squared plus I squared. Sum of I squared R and I squared capital R. This is external and this is internal resistance. In a charging process, a charge carriers supply the energy to the battery in opposite to the EMF arrow. Conservation of energy requires that the sum of EMFs and the potential differences around the closed loop vanishes. So EMF supplies the energy and resistors consumes the energy. An EMF source is defined in terms of the work it does on charge carriers. This is an example considering the two EMF devices connected in series in opposite polarity. So it is straightforward to follow this calculation. So please do it yourself. Multiple loop circuit. This is an example of multi-loop circuit. This is a loop, this is a loop. In comparison with the previous case of single loop, this only possible loop is a single one, and there are multi-loops. This is a loop, and this is another loop, and there is another big loop. So we can construct the three loops in this multi-loop circuit: branch, junction, and loop. A branch is a circuit element having two terminals. So this is having two terminals. EMF device, this is a branch because there are two terminals. And resistor has two terminals. Capacitor has two terminals. Inductor has two terminals. So any circuit element having two terminals is called a branch. A resistor, capacitor, battery are branches. A junction node is a point where two or more branches meet. Two or more branches meet. Junction. A loop is any closed path in a circuit. Loop is any closed path in a circuit. This is a loop, this is a loop, and this is another loop. A multi-loop circuit consisting of three branches. Left-hand branch. First, we consider these three branches that are resistors. The circuit also consists of three loops, this loop, and this loop. A and D are two junctions. A and D are two junctions. B and D are two junctions. A branch connects any two junctions. Branch. This is a branch that connects two junctions. This is a branch that connects these two junctions. This is a branch that connects these junctions. Every branch has a single current. Every branch has a single current. Every branch has a single current. The direction of this arrow is chosen arbitrarily, and once you fix the direction, you must stick to the direction, because the current I depends on the direction. The sign, the magnitude will be the same, but the sign will be determined in a different way once you flip the direction of the current. Every junction has a constant of junction rule. Junction rule. Current conservation is needed. So current, for example, at B, I1 is I1 I1, this is I1, and I3 is going out, and I3 is coming in. Therefore, I2 equals I1 plus I3. Junction, Kirihof's current law. It's the sum of currents entering a junction is the sum of the currents leaving that junction. Sum of currents leaving this junction B. For example, we could have chosen the junction D. In that case, I is coming in, I1 is coming in, I3 is coming in, and I2 is going out. Therefore, again, I1 plus I2 is 3 is coming in, and coming out I2. So these two rules are redundant. We need only a single one, either this or that, because they are equivalent. Junction rule is a consequence of charge conservation, and charge is not accumulated anywhere. loop to the left-hand loop, counterclockwise, loop, the left-hand loop, this loop. There's a EMF device, E1. If you follow this direction, then you decrease the potential. I1, R1. And you follow this direction, opposite. This loop direction is opposite to the current. So you have I3, R3, but the potential increases instead of decreases. And you return to the same point. So loop to the left-hand loop counterclockwise from B here. E1 increased. Follow the I1 minus I1 R1. You cross across the resistor R3 in opposite direction with respect to the current I3. So plus loop to the right-hand loop counterclockwise. Counterclockwise from C. From C here, you follow this direction counterclockwise. So from positive to negative, you have decreased the potential, E2. You follow this direction. Now I3 is a parallel. So I3, R3, you decreases the potential. And then you followed I2 again. I2, R2, but you decrease the potential because you follow the direction of the current. Hence, you have two equations. Now you see this equation is I3, I3, I2, R2 minus E2. So this is the same as this, and this equation is same as this equation. So you have constructed two equations. You can consider loop to the big loop counterclockwise from B. Counterclockwise from B, you follow this direction. First, you pass this battery. Following this direction, you have increased the potential E1. And then you follow this direction parallel to the current. So you decreased, let us write E1 minus I1 R1. And then all the way through here, you reach R2. Again, you follow I2. So I2, R2. And you go ahead to cross this battery but the direction is decreasing the potential each, and we return to the same point, so equals 0. Let's see reference E1 minus I1R1 minus I1R1 minus I2R2 minus I2R2 minus E2. That's correct. You have obtained the three equations. But only two loops are linearly independent among the three left, right, and big loops. Consider a circuit with B branches, J junctions. You follow this. This is a general rule following from mathematics. And this is an application. Okay. Okay. Let's continue to consider the RC circuit, the remaining part before here until page 13. It is straightforward, so please follow the text and study by yourself. Let us consider RC circuit. This is the most important part of today's class. We have a resistor and capacitor connected in series. In between, there is an EMF device. Capacitor has a formula Q equals CV. Q is amount of charge, so if the current flows in and positive charge accumulates, and negative charge, equal amount of negative charge accumulates in here, then the potential difference between the two parallel plates becomes V, and C is the capacitance. Capacitance. If you connect this switch to A, then from the positive terminal of the EMF device, current flows and passes the resistor, and the charge is being accumulated. So there's a potential difference appears. As time goes on, the capacitor becomes fully charged. When we reach Q equals CV, or V equals Q over C, when this potential reaches the exact amount of EMF, then the current stops. At that stage, this potential gain becomes potential loss, and that equal amount, this is a positive terminal, and it becomes, this capacitor has positive charge and this negative charge, and this is E, and E becomes Q over C, where C is the capacitance of this capacitor. But during this time, until it reaches, we say this is a fully charged state, the current flows in that case, the resistor consumes the energy. Let's study in more detail. On RC series circuit, this is called the RC series circuit, consists of a capacitor of capacitance C, an ideal battery of EMF E, and a resistor of resistance R. Closing switch S on A, closing switch on A, charges C. When you close the switch, then C is being charged and the current flows passing through the resistor. When the circuit is complete, so when it is connected, charge Q in C increases as I flows. And the potential difference across the C is following the formula Q equals CV. When C is fully charged, the potential difference between the two plates of the capacitor must be the same as the potential difference between the two terminals of EMF. That means that the potential difference between the two terminals of the resistor vanishes. If the potential difference of the two terminals vanishes, because Ohm's law V equals Ohm's law VR equals IR, there is no potential difference in the resistor when C is fully charged, then the current must vanish. The equilibrium charge, that means when the capacitor is completely fully charged, then Q becomes CV and V is replaced with the potential difference of the EMF device. Charging a capacitor. We studied the relationship between among charge Q in the capacitor. We see the potential difference between the two plates of the capacitor, current I of this circuit during the charging process with the initial condition Q0 equals 0. So let us consider the case when the capacitor is completely discharged at t equals 0. So loop rule states that when the circuit is completed, we have a single loop circuit. We follow this. We have plus E, follow this line. You have I, R, decrease of the potential. And this is a plus, so positively charged, negatively charged. So there's potential loss, Q equals CV, Q over C, we have negative sign, because if you follow this direction, potential decreases from plus to minus. And we return to the same position equals 0. So this equation is written in here. Here, minus IR, potential loss from the resistor, minus Q over C, that is a potential loss when we cross the two plates, from the positively charged plate to the negatively charged plate. The loop rule is the first order linear differential equation. Let's see. This one, IR plus Q over C equals E. Let us divide both sides by R. It's I plus Q over RC equals E over R. Now the current I is the time derivative of charge. So this is first order derivative 1 over RC, a constant factor Q plus E over R. This is that equation. This is the first order linear differential equation. And we have non-vanishing right hand side, non-homogeneous linear differential equation. We can find out the solution. First, the solution must be Q of t is QP plus QH. That means QP is a particular solution. Particular solution can be obtained by substituting the constant value. That is, QC equals constant. Then QC dot is 0. So if we substitute QC in this equation, first term vanishes. The second term is QC over RC equals E over R. So R cancels. So QC equals CE. So particular solution is CE. Oh, QC, QP. Q particular. Q particular. Q particular is equals CE. Equals CE. Now, next we consider the solution for the Q over RC equals 0. This is a homogeneous equation. Homogeneous equation has as the solution. This is the first order equation. First order equation. So dq over dt equals minus q over rc. So this is dq over q and rc dt. So we can integrate this one. If we integrate, you have log q equals minus rc t. So Q of t minus, oh, if you integrate this plus some constant, and Q, actually this is Q of t. Q of t is exponential plus constant. If we substitute t equals 0, q0 equals e to the constant. Therefore, you can say q of t homogeneous equation solution equals q of 0 times e to the minus rc over t. However, we have particular solution. We cannot say it is a q0 exactly the same as q0. Let me just say for simplicity, it is something like some constant c. C is confusing. Constant a. So therefore, we have a particular solution, CE, and the homogeneous equation solution, A T over RC. Okay, so if we substitute Q0 or T equals 0, it is CE, and this one is 1. So in our problem, Q0 is 0, initially completely discharged. So A equals minus CE. Substitute this result in here. We find that CE 1 minus exponential T over RC. This is the answer that is given here. The explicit time-dependent plot of the charge is 1 minus exponential T over RC is increasing arbitrarily close to Q max, that is a CE, because as t goes to infinity, this approaches 0. If I take the derivative with respect to time, what I obtain is this constant term vanishes, and remaining piece CE E minus RC T dt. C is here, and negative sign, minus 1 minus RCT, no t, e to the minus RCT. So this is CC cancels, E over R e to the minus RCT. This is the current. The current decays. At t equals 0, I max, maximum value approaches. I max is E over R. So at t equals 0, this system is the same as this. So because Q equals 0, there is no charge, there's no delta V equals 0, so it does not contribute to the system at t equals 0. But at t goes to infinity, this one disappears, and charge is completely charged, the capacitor is completely charged, so the potential difference between the two plates of the capacitor is the same as that of the EMF device. As t goes to infinity, the system as t goes to infinity, it reaches identical to this system. So I equals 0. Here I equals I max, Q equals 0. I equals 0 and Q equals Q max. Because we have obtained the current of the system, multiplying resistance R to here, we find the potential difference between the two ends, two terminals of the resistor. So as t goes to 0, at t equals 0, VR equals E at t equals 0, right? But as t goes to infinity, the exponential becomes 0. That means VR equals 0 as t goes to infinity. So goes to 0. In a similar manner, the potential difference between the two terminals of the capacitor is obtained by Q over C, or it can be obtained by E minus VR of T, because sum of this VR of T plus Vc of T must be E. So in summary, we have these results. Time constant. We have a term T over RC. Exponential is actually the sum of k runs from 0 to infinity, x to the kth power, and k factorial. And this is a pure number. And this is power. Hence, in physics, any number can be added only if they are of the same physical dimension. So x can be added to x squared only if they are dimensionless. For example, second cannot be added to second squared. In mathematics, it is s1 plus s, but In physics, one cannot add 1 second plus 1 kilogram. Not defined. One cannot add different different number, different dimensional quantities. It's impossible. That means exponential function is a linear combination of different powers. Therefore, in physics, this x must be dimensionless. Dimensionless. Because it is dimensionless, t has the dimension of time. Rc must be of dimension of time. So we use a special notation tau. This is tau, Greek letter tau. Tau is defined by Rc, resistance, about the product of resistance and capacitance. It is a number of dimension of time. And it is a very important number that specifies the characteristic of the RC circuit. So we have a special name. RC is the capacitive time constant. Capacitive time constant. And this one is an argument of an exponential function, and exponential function has a special values. E, the Euler's number that is defined by the limit of this expression. Here it's wrong, n goes to infinity. We have special values. For example, 1 over E equals like that. 1 minus 1 over E, so like that. So memorize approximate value of these. So these numbers can be used to identify the system. The RC is scale of time. So just to follow these problems to find out how the scale, the time scale RC, this was capacitive time constant, is used to specify the system. And the number 5, 6, and remaining problems are all can be easily solved by considering the theory that I have just described, depending on the RC circuit. So, problems. Consider RC circuit whose circuit equation is given by t equals 0, capacitor is uncharged, and at t the capacitor is charged at Q0. This problem asks you specify the energy saved in the capacitor and the energy being consumed by the resistors. Okay, that's it for today.